Okay, yeah, so I'm going to talk, like we mentioned, about Counterfactual. Some just quick notes. This is like a technical talk, right? And so what I've found when I've been in audiences of these kinds of talks is it's super easy to get lost because someone speaks too fast or they say something that's confusing, that some term that you didn't hear before. So I just like to set the tone for the very beginning. If there's anything at any point in time where you're like, I don't get what the hell this guy's talking about, just please put your hand up, just ask the question no matter what it is. Because it's almost with certainty someone else is asking the same question. Just as a quick note. Anyway, so Counterfactual is an open source initiative to make secure off-chain applications easy to build on Ethereum. Like you mentioned, my name is Horne. I run a company called L4. We generally help out in the ecosystem. We work on the software. We help run East Global. If you've been to an East Global hackathon before, that's largely out of the work that we've been doing in partnership with some other friends of mine. And I'm also the more Counterfactual, which is a clearly separate thing, which is that we're trying to separate from L4, but over time I got a bit confused. It's the open source project, which I'm about to show you today. So what I'm going to talk about, just quickly, what are generalized state channels, just to get that part cemented. 2, what Counterfactual specifically is in relation to people that are interested in state channels and how can you use it, and then show a demo of it working today. So that's the basic rule. I want to show you why this stuff's interesting and how it works. So very quickly, background so you can understand what state channels are at the simplest level. Most people have already seen this, so I'm going to go through it fairly quickly. But any questions, just ask. So a payment channel is this concept in a blockchain where you have your blockchain, and the idea is that what you want to do is you want to lock up some amount of your money, some amount of some other person's money, into some contract which says that this amount of money is in the contract, and if at some later point in time you can both attest, both Alice, Bob, both depositors, that there's a later state, a later balance differences, that is the latest state, and you should be able to withdraw it back to the chain with that state. So the way it works is, as time goes on after these 2 initial transactions, 2 people, say Alice and Bob, literally just exchange messages to one another. It could be over any medium, it could be text message, it could be WebSockets, it could be Firebase, it doesn't matter. You're signing messages back and forth for the people that made the deposits that pertain to new updates. So from version 0 to version 1 to version 2 and so on and so forth. And whenever you're tired of doing this up until the nth increment, you say, great, we're done with this. The last version is n, and so let's go back to the chain and just get our money out. And so then Alice gets Alice at version n, and Bob gets Bob at version n. It's very straightforward. So that's what a payment channel is. This is exactly what runs on Ethereum, on Bitcoin. This is the Bitcoin Lightning Network. Essentially, it comes from that core primitive. The idea being that you update balances between 2 parties. Because this is Ethereum, we can do a lot more than that than just balances between 2 parties. We can do arbitrary state. So this new term was coined in Ethereum called state channels. And in state channels, this is what the naive setup would look like. In state channels, instead of just having the state of the contract being A val and B val, you can have state, non-state, whatever. Just basically say you can have any kind of state. And this can be anything you can store on the Ethereum virtual machine or in general on Ethereum. So it could be bytes, it could be 2 units, it could be an address, it could be whatever combination of state you want, instead of just A val, B val. So that's the first thing when you talk about state channels. It's not just payment amounts, it's arbitrary state. But otherwise, everything's exactly the same. Deposit in, update the state by signing messages with each other that you both agree on, and at some point withdraw it back out. So if you're familiar with how ERC20 contracts work, for example, the actual thing that you own is not some, like say, a DAI token or maker token that is stored in your account. You actually just happen to have an address that for another contract you own some token in that contract. And so in this case, what you could be trading is a signed message that says how that other contract storage has changed. That's a strict aside on that. So what are generalized state channels? And again, a quick note on these state channels here, that when you're withdrawing the state, you can add some arbitrary Ethereum code when you get it out. So for example, if the state was a tic-tac-toe game, you could say whoever won the tic-tac-toe game, if the board has an X with the cross, that person gets some money. Instead of just being send A val, send B val. So what are the generalized state channels? It's this fancy term. It's basically, if you took the idea of state channels and you took the power of Ethereum, instead of just having this naive improvement from how payment channels work on Bitcoin, what could you do that's more interesting? And this is how I like to show it. It's the same setup. You have some number of people that start with 2, Alice and Bob, and what they do is they deposit something on chain. It could be ETH, a token, doesn't matter, into a contract. But the different thing that you do in this case is as time progresses, you actually can do things like this. You can assign the state that you deposited, let's say it's ETH for the sake of example, to some other application, where the application logic itself is something that is defined within the state channel. Right? So, for example, you can say, we're going to put our ETH to a contract and install an application for tic-tac-toe, where the winner of the tic-tac-toe gets some amount of money. And of the initial deposit that we put in, some sub-deposit amount is the amount that we're going to allocate to that game. And if you look at it this way, then it doesn't really make that much sense to prohibit the number of times you do this. You could have 2 applications. And you could do this, continually as many times as you want. With the same basic setup, you put some money into a contract, but instead of just signing an update that says, this is the latest state, this is the latest state, this is the latest state, you sign more complicated types of agreements, which Ethereum can support because it has this smart contract language, that pertain to this kind of situation. You have multiple applications that you're opening, with each application itself having some substate. So there's an enormous amount of detail, which is the goal of the next part of this talk. But this is the key setup. And again, as time goes on, if you want to withdraw any of that back to the chain, you can just simply submit the latest state for one of them and get money out pertaining to how that particular application denoted results an outcome. So you can imagine in the demo that I'm going to show you later, this application on the left could be tic-tac-toe, this application on the right could be like a dice rolling game where the higher 2 count numbers is the winner. It doesn't matter, as long as you can codify on the Ethereum blockchain. So does this make sense so far? Yeah, great question.
Can you do it? Can you definitely do that with applications that don't exist yet?
Yeah, so the most important thing is that on Ethereum you can sign arbitrary messages, right? And what's important is that you're signing messages that could go onto the chain in the future. So at that level of abstraction, just for that statement, you can sign a message which pertains to any arbitrary Ethereum operation, which could include creating a new contract on the chain and then executing that code. Now, if you're going to implement a framework, which I'll show you in a second, you wouldn't want to go to that level of optimization, but you could totally do that. So these applications, the most optimal way would probably be have the logic stored on chain so you can reference it. But there's no actual motion that needs to exist on chain saying that Alice and Bob are playing tic-tac-toe. It doesn't need to exist. Because all that needs to exist on chain is that Alice and Bob put money into something. Cool. So if you didn't get all the technical detail of that part, there's a blog post which goes into like the basic idea of this and how it's different from Plasma and all these other constructions. Which, if you're looking for an introduction to layer 2 technologies like what this is an example of, I'd recommend reading this article. It's extremely well written, like 20,000 claps on Medium. It's a good article. So yeah, before I move forward, any questions? Or should I go? Questions?
Would you still have to do some relative amount of work on chain to verify all the steps that happened? That doesn't make sense. So you're not saving as much as that.
Yeah, you don't have to do that. So the question is basically, this is fancy, but don't you still have to put on chain some kind of contract or something that can verify all the steps that happened while you're off chain? The answer is no, because all that really matters is that the 2 people initially agree on the outcome. If they disagree, it's a different story. But if they agree on the outcome, all you need is to say that it said, you and I agree that you want some money, and so send me the money. You don't need to even reference the application. But I'll get into that later when we talk about this use and stuff like this. So, anyway, so what is counterfactual in relation to this general project? You had a question, that was quickly.
Yes, so I have a question maybe not related to this, but just curious, like I kind of know it's payment channel is state channel concept, but I just kind of came out to the question is why historically the channel is 1-to-1?
Why historically the channel is 1-to-1? Yeah, my understanding of this is just because this is the way this is the constraints that Bitcoin put on it, and so when the Lightning Network was kind of invented, they didn't really have a way around that. This is my understanding of it. And in Ethereum, they just copied the Lightning Network. At least most people did, and so they started with 1-to-1.
But a lot of the application, for example, in the game, let's see, Texas Hold'em, if you want to play multiplayer games.
Yeah, there's plenty of other games. Yeah, I'll show you something like that in a bit. So what is Counterfactual? First and foremost, most important thing that you get out of this, it's an open source project. It's not a company, it's not a token project, there's nothing about this that is like a for-profit initiative. We're simply just a bunch of people that are enthusiastic about Ethereum that want to try and take the best standards from great people that have been talking in places like this and posting online, but all these phenomenal ideas, and actually get them into production such that we as a community can move forward. That's step one. The vision that we have is that applications of the sort that I've been implying so far in the talk become the norm. It should be simple that if someone wants to write an application that's decentralized, that it should be as close as possible to the user experience of an application that would otherwise be centralized. There shouldn't be this weird in-between layer where you're using MetaMask for every possible step and you have to keep track of this bizarre state. It should just act and behave like a regular application. This is the goal of Web3 and of all this decentralized application stuff. We don't need to have all this weird in-between technology. That's just inefficiency. So the goal is to get to a world where decentralized apps are just as efficient and easy to use as centralized apps. The mission of the project is to build all of the software and the tooling that we need and to get the community together to make this happen. So, we're building 3 core pieces of infrastructure. I'm going to refer to them briefly in the next slide, and then show you kind of how it works, and then go in more depth later. So, it's more like 3 layers actually, and 4 kind of core software pieces. But generally, the way you can look at it is like this. There's, at the very top level, it needs to be the case that anyone that wants to interact with an application that's kind of a layer 2 application, there needs to be a very easy entry point for them. So if you're looking at how an application works for Ethereum right now, you use web3.js or ethers.js, or in some way you make function calls from your client, it's a phone or it's a browser, or whatever it might be, to an Ethereum node. And you say, like, I want to call this function on this contract, and you interact with it that way. With layer 2, there is no like contract you call a function for. Instead, you're kind of interacting with other counterparties. And so fundamentally, you need a different kind of client library, which is the first thing that I'm referring to here. Secondly, you need to know how to communicate to those counterparties. In the pictures I showed earlier of Alice and Bob talking to each other, in order for Alice and Bob to talk to each other, to say things like, I want to install this application which doesn't exist yet, and it could exist maybe if we were ever getting a fight in the future, and I want to make sure that if we do get into a fight, you can't reach me in these bizarre ways. That's a long, complicated series of messages that you need to exchange. And so we've defined a set of protocols, which are just schemas for how basically you talk to another person, another set of people, that define precisely how you can do this in an easy, intuitive, and safe way, most importantly. Obviously, you need software to run all that because it's complicated, and so we have this client mode software that we've written. And of course, the last part, the reason why Ethereum is useful here, is that if you're interacting with other parties and they don't behave, you need a way to say, hey, this person's not behaving, Ethereum, save the day, and get my money out. And so we've built a whole bunch of actual adjudication mechanisms and contracts on chain that are the basis on top of which the protocols are defined on, such that you can always get your money out if the other person's not behaving. Because that's the whole point of this. You don't need to trust anybody. So great. So demo. So I'll show you this. I'll show you what we just released recently. And let me just make sure I get the video up here. Okay. I won't risk you sadly. So, okay, so this is the demo video. So I'm going to kind of walk through it. Basically, let me give some context. So this is something that we just released, I don't know, a week, 2 weeks ago, something like that. There's a lot of promise in there. This is a demonstration of everything I just showed you in a production web application, where you as an individual user will get a very nice user experience, where you're doing all kinds of off-chain things. You're going to play tic-tac-toe, you're going to play this dice rolling game I referred to earlier, and at no point are you going to have to interact with the blockchain after you've done this initial deposit step. So if you remember from the diagrams earlier, you deposit, Alice deposits, Bob deposits, and then you do all this crazy stuff where you do off-chain applications. You're going to do the deposit step, and then you're going to do the off-chain applications. And this is a web application which shows that stuff all working in production, at least on a testnet, with real world code today. So I'm going to kind of buffer my way through this and explain it as I go. So first thing, you're on this landing page, and what we have done is we've set up this this website such that you as a user can create an account with us. So the premise here is that we, like the team behind Counterfactual, not the company or anything, just we are doing this as a demonstration, have set up a server which is going to behave like Bob. It's going to behave like a state channel user, and you just navigate to this website, and you're going to behave like Alice. And what you want to do is you want to play against the other people that have connected with Bob, say Charlie or Ignis, whatever the other ones are. And you want to basically play arbitrary applications against these other people. So Bob has a server, and he's made this website available to you. So what you're going to do, depending on how fast this goes, is you're going to click the create account button, which is just a regular Web 2.0 thing at this point. You're just making an account with the server that Bob's exposing. So this is just a RESTful server. And after you, and we've used Web 3 for authentication, but after you click create account, what it's going to do, you sign a message saying that you are who you are. This part is not state channels related, it's just authentication related. Bob's going to get that message, our server, and it's going to create a state channel for you. So in the background, it's going to actually deploy that contract that I showed in the diagram earlier, within which you're going to make a deposit. So this is the core contract that Bob is going to put money into, and then you're going to put money into. So what happened very briefly there is the server, us, Bob, made a contract, put it on chain, and said, okay, I'm ready to go, let's make a state channel together. Phase one of a state channel is put money in the state channel. So what we're going to do first of all is us, as the browser user, we're just going to put in some amount of money. I should have sketched this up by 2.5% or something, enough time. So I'm going to put in some money. I sign a regular MetaMask transaction that authorizes the send of 2 ETH. So this is very standard at this point. Just put some money in the contract. And wait for this to happen. As this is happening, the hub server, Bob, the second party in the account from the state channel, is also going to deposit 2 ETH as well. So that's what you're going to end up in a situation where you have put 2 ETH into a state channel, and so as a counterparty, also into a state channel. And this counterparty, which is us running the service, has done this with like hundreds of other people. And so what you have is a state channel network that is kind of coming out of this. So this is just waiting for blocks to basically get mined, because you're putting transactions and you need to verify that they actually get mined. And then when it's done, all of a sudden, boom, these 2 buttons pop up. What we're saying is, hey, if you want, now that we have a state channel, the hub and you, the person in the browser, you can now play against all the other people that have opened state channels with us. You can play these 2 games. These are the 2 games we happen to support on the web UI. And from this point on, you don't have to use Ethereum. You don't have to sign any transactions. You don't have to send any transactions to the blockchain at all. You can just use these applications. This is me just quickly showing kind of on either scan that these transactions actually get mined, the money going into the contract. We can skim past this. And you'll be able to see, okay, what you can do is you can open an application, it's a tic-tac-toe. And what you want to do is you want to play against somebody else. So what you're doing here is you're saying, hey, I want to play against somebody else. I'm going to bet 0.01 ETH, and I want someone else to play against me. We have a bunch of matchmaking and whatnot, so what it does is it matchmakes you against another user that's ready to play against you, also willing to put up 0.1 ETH to bet that they can beat your tic-tac-toe, and then open the game live in your browser to play. And you can kind of assume how this is going to go. I'm talking over in this video, that's why there's a little bit of delay. You place your X, you place your O, and eventually you win the game, and you go to see in a second, if the screen is not put up, that your balance has gone up by 0.01 ETH. So you're very happy. And so what just happened? So what just happened is you opened up a state channel with somebody else with whom you have not even been acquainted with at this point. It's just some other user that happens to have gone to this website in the past. And what you're doing is you're actually signing commitments with them pertaining to an off-chain application, the entirety of which is secured by the protocol we defined, which is itself secured by Ethereum. So these applications are 100% trustless, and no point where you're at risk of losing your money. In fact, if the person on the other end had not placed their X at the last point or didn't play the game with you, you could always have just gone to the blockchain and said, okay, get my money out. This person's not responding with me, and there'd be a fair communication to ensure you get your money out. And just for the sake of showing the second example here, You can also play this dice rolling game, which is just an example of randomness, where you can go to the game, you can roll your dice, what you're doing, you're just sending equipment over, you're sending a message over to the counterparty is going to acknowledge it and send their side message to change to their dice roll. We use kind of this randomness technique, and you can see that the opponent rolls a higher number than you, so you lose, and so your balance will get recommended. So that's kind of like there's a lot of stuff going on there. So maybe we should actually get some questions. That's kind of the most important parts of the demo. So yeah, questions?
Yeah, what's the format of the transactions that are going between players? Are those like securities transactions?
So the way I described it earlier is that this software where Alice and Bob need to speak a particular protocol in order to do all this stuff. The protocol defines specific types of messages that you need to sign. That if your counterparty at any point in time were to be unresponsive, you could take those messages, which are your transactions that could go to the chain, and you could put them to the chain, and what would ensue from that period on would be an adjudication of this particular application. And your opponent would have a chance to say, well, this is the latest state, you would have a chance to counteract that and say this is the latest state, and there's basically an adjudication mechanism ensues.
So does that mean so for this dice rolling game, there has to be some code on chain that can interpret that state and resolve it?
Yeah, that's exactly right. And that's the lowest level on that diagram, really the 3 square diagram at the bottom. I call it state resolution.
So that goes generic to all the state chains that
Yeah, I realized I wasn't repeating the questions, but basically all state channel implementations, period, need to be able to resolve what are commonly called disputes. We also call them protocol deviations. Basically, you're relying on your counterparty to always be online. If they're not online, you have to be able to do something about it. And to do something about it, you have to go to the blockchain, and the blockchain has to adjudicate you fairly. The protocols are defined as specific messages you send back and forth, which represent signed transactions, which are exactly those things that you would go to the chain with. That makes sense. Cool.
Are you guys using peer-to-peer messaging between the players in the game?
No, in the demo it's 100% centralized just for efficiency. So the question he asked is, are we using peer-to-peer messaging? The answer is no, just because in this demo, it doesn't really add any benefit from what we're trying to show. However, in an ideal, perfectly decentralized world, you would use libp2p or some variant of that. But at the moment, it's ironically it's using Firebase for messaging. But yeah, go ahead.
Does the messaging between 2 players go through the server message?
Yeah, so you're asking like, how does messaging work? It's using Firebase in the demo. So it goes through a server, yeah.
Let's say the question is, that's okay.
Alright, I'm okay with some friends. Maybe I should cap them to 1 or 2 each. Yeah, so that's a demo. This is the video demo. So I'm gonna just pull up my presenter view down here so I don't keep looking at it. So diving into what we just saw. So I'm gonna explain bits and pieces of it. So this is gonna be like ELI5 explanation, right? So you just saw this screen, right? Where you are looking at applications, then you can play it. What you were actually seeing in terms of now, me getting into the bit of the detail of the technology that we've implemented, what you actually were looking at was 2 different kind of, I guess, multiple parts of tech stack. One is we kind of have a bit of a state channels wallet emerging in this demo. In the demo site, it's actually running the node software that I alluded to earlier, which is the thing that actually is signing all these messages that you are passing backwards and forwards with your counterparty. You can see that I've kind of highlighted this part of the browser because it's actually the case that the other part is just an embedded iframe with which the other part is simply having a bit of a iframe post message messaging back and forth with. And the application is actually using an API to communicate to the external wallet environment, which is running the node software. So that kind of looks like this, where the application itself, tic-tac-toe, written by some developer, is able to say, hey, layer 2 wallet, I want to install an app. I want to draw one of those dotted contracts. I want to do one of those things. And so it says to the node, I want to install an application, let's go. And then the wallet will go back after it's done its job, which is execute the protocol fairly and correctly, and say, hey, the app has been installed, now we can begin actually using it. And someone asked earlier, like, isn't it the case that you need to be like sending multiple transactions this whole time, or don't you need to put stuff on chain eventually anyway? And the answer is no. The only things that you need to do are deposit and withdraw if you're ever going to interact with the chain. So you saw that in the demo I showed you earlier, the deposit step, where you actually have to say put in 2 ETH into the contract with the counterparty. And I didn't show the demo just to save a bit of time with the withdraw feature. But if you ever want to get money out, similarly, you just sign a message with your counterparty saying you want to get the money out, put the transaction on the chain, and you get your money back sent to you. And so this is kind of this nice, clean separation between layer 1 and layer 2, and dApps generically speaking, where they can use layer 1, they can use layer 2. Preferably they use layer 2 because it's much more efficient and fast and whatnot. And we try to design everything with this in mind. And we're going to go into some of the details of this in a bit. So just like as a code example, in the tic-tac-toe code, we use React. And the actual method handler, like when we click X, like in the bottom right hand corner, this is the method handler. And so what you're actually clicking is, okay, this row, this column, tic-tac-toe board, I want to place X. And this is as simple as you can imagine. Right? You literally just send an awaitable call to the tic-tac-toe game, an object that you would have that essentially is mocking calls to the wallet, to the node, saying, hey, I want to take an action, I want to place X at this point, and whenever you're done doing all of the protocol business and you sign messages for the counterparty, get the new board state back, and let me render my UI with that. This is really as simple as it gets. So traditionally, this little snippet of code in Ethereum has been like, thousands of lines of like smart contract code and calls to contracts, and you have to wait forever for every single X and O to be placed on the board, and you have to pay money for this. This is what it gets reduced to in layer 2, which is a pretty epic reduction. Quick side note, by the way, because I've been showing you this separation between layer 1 and layer 2. As a quick side note, we've been working with MetaMask such that that separation is not like our iframe container. It's actually within our wallet that, at least in this space, normal people that works are using. And we already have this working today, where inside of MetaMask itself, we've been working very closely with them to get a layer 2 environment, essentially, where you can start installing these applications like tic-tac-toe and the actual in-game and things like that, just natively within MetaMask. So every single MetaMask user will have a similar experience to the demo you just showed, that I just showed. The only thing you have to do is deposit money in, and you navigate to your website that supports the API I just showed you, and everything's off-chain. So the world that we can get to is not that far off. Some other stuff. In the browser that I was showing you, obviously, if I'm signing messages, you're signing messages, we can't really rely on Ethereum for all of the state management anymore, because we don't have this global decentralized state machine for all Ethereum apps. Now we actually have local state that I need to keep on my person and you need to keep on your person. And so in the demo, if you want to play with this, I'll show you the link later, you can inspect it. We're actually storing all of the state locally. So all of the signed messages that we've been signing back and forth with the counterparty, all of which happen behind the scenes in the actual node software, the private key that we injected in, this is an ephemeral key that lasts a small amount of time. You can see it all in there. And if you want to look at some of the details, I won't go through all of this now, but you can see we have designed everything in the tech stack to be able to kind of abstractly represent arbitrary applications. So I'm not going to go through all this, but just some quick highlights. We can see that in the app interface part of this JSON, we can see that we actually keep track of the encoding of the state, and it's simply using an API encoder v2 struct. So anything that you can represent with an API encoder v2 struct, which if you don't know already, is basically just it's a struct class in Ethereum. It can represent arbitrary data, and it can be nested, right? You can have bytes of bytes of bytes, and you can define arbitrary data structures with it. You just simply keep track of that. You keep track of the contract that represents the logic, which I'll talk about the logic in a bit. And this can represent literally any arbitrary state machine you can put in Ethereum. You can see in the corner of the latest state part, we keep track of the data is stored for this particular app that uses that encoding. So who's Alice, who's Bob, how much does Alice have, how much does Bob have? It's using big numbers there. And again, arbitrary Ethereum data structure can fit into this, and it's very nice and clean. So anyway, so we're back at the laptop, and yeah, I can check all that for you. So what actually happened here is I kept saying that it's me playing this game, there's Bob in the server, and then there's also like other people we're playing against. The actual situation here is there's two users, and I already asked some questions that will answer some of the next parts. But they needed to basically message each other in some way, right? So a quick aside, for people that are interested, this part we're going to go a rabbit hole if you're really going into it, but I almost want to go to the high level. If you want to play against somebody else that doesn't have a channel with you, which I did in the demo, right? I opened a channel with us who have a server, but when I play tic-tac-toe or the dice rolling game, I played against some other random people, right? So let's say Bob is the person I played tic-tac-toe against. There's no actual channel here, so how did I do that? Well, the answer was, and I kind of gave it away already, is that we were running a hub. We were running our own server that acted as an intermediary between you and the other person. And this is the same scenario that you're familiar with the Lightning Network. If I want to send you money, and I don't already know who you are, and I don't have a channel with you, then I need to go through somebody else. And it's the exact same thing with Ethereum. You already have a channel with the hub, which is what we did at the beginning of the demo when we made that account, right? And then you can just open up a meta channel with the other person that you haven't met yet, which the dotted line represents no Ethereum transactions at all. The hub can collateralize the usage of the application. So in a sense, if I win tic-tac-toe against Bob, the hub will send me money, and Bob will send the hub money. Anyway, that's the quick aside. So the cool part about this from a technical point of view is that the hub software was literally the same software that was running in the browser. It's literally the exact same software. The only difference is that because it's a robot, right? It's software and not a human clicking buttons. There was a couple event handlers that we had written and implemented, such as, hey, if I deposit as a user, the hub will auto deposit as well and put some money in to collateralize it. And additionally, if I want to play tic-tac-toe against some other person against the hub will automatically say, yes, this is fine, I will collateralize it, right? But it's just software. It's the same software as the one running on the client, which you're very familiar with if you've been looking at other layer 2 solutions in other places, say for example Lightning, where they have LND and Eclair and these things, which is the same software, just used in different environments. So the way that we actually played the game against the other person was that we said, hey, I want to propose an installation. They acknowledged it. Once we were both okay with it, we went to the hub and said, hey, I want to install this virtual application. The hub said, this sounds great. The counterparty said, this sounds great. And then the game was collateralized and I got to play it. So yeah, that's an enormous amount of detail there. So I'm about to dive. I guess, well, how many minutes time? That's my question.
How long is your talk going to be?
20 minutes.
Okay, we've got like 10 minutes.
Okay, so I guess I'll take just one quick question on that part. Maybe like the one that people think is the most pertinent. Fine.
Does that mean the hub has to provide like liquidity for the person?
Yeah, exactly right. Yeah, so the way it works from the hub's point of view is that, let's say we want to tic-tac-toe against somebody else. It needs to be the case that if I win tic-tac-toe, I get money. And the only way I can get money is from the hub, because I only have a channel with the hub. And so the hub needs to be able to lock up some amount of their money that will either be given to me, or simultaneously with me locking up my money, will be given to the hub, depending on the outcome of the channel. So if I won tic-tac-toe, the hub will give me money. If the other person won tic-tac-toe, I will give the hub money, and vice versa on the other side of the relationship. So both I and the hub will lock up the amount of money that we have in the game. So if it's a game for 2 ETH, I'll put in 2, the hub will put in 2, and on the other side, the hub will put in 2, the other person will put in 2. So the hub has to lock up twice the amount. Yep.
How much gas does it cost to close out the channel in an adversarial situation?
In an adversarial situation, so it's hard to answer that question because there's several types of adversarial situations. And I also don't have like the simplest scenario.
Where's the worst case scenario?
Oh, the worst case scenario is the briefing scenario where I play tic-tac-toe and I put an X and the guy doesn't respond. So then I'm like, I go to chain because I want to get the money out, and then he responds all of a sudden, and then he makes his move, and then I'm like, okay, let's keep playing, and then I play again, and he doesn't respond, and he comes back and makes his move. So you can keep going forever and ever. That's the worst case scenario. That's a lot of gas costs. If you're looking for a number, it fits within a block. probably less than half the block size if we can optimize it. I don't have the exact number of like, I don't have like a buzzword ready number though.
I was wondering because I recently was going to put payment channels with my project and realized that was kind of a wash with gas costs. Usually costs a lot more than transfer bill.
Yeah, I think there's a good paper you might want to read. I think it's called Battleships, something like that, by Patrick McCrory, which does like an empirical analysis of playing battleships in the blockchain. He concludes that, yeah, it's kind of frustrating to do these kind of applications because in the adversarial scenario, you end up paying a lot of money. So there's like this lower bound that ends up being higher than if you were to play it on chain, like for a very basic app. There's a lot of stuff that's missing there. I don't want to get into too much detail here, but there's a lot of stuff that's missing that can really lower that cost dramatically. So maybe we should chat about that later. Okay, yeah, cool. So I'm going to quickly go through some of these parts just to show other interesting things that we built and kind of how it all pieces together. So I talked about this tech stack earlier, the contracts layer, the protocol for state channels, and the application library on top. I'm just going to quickly go through each of those sections a little bit. So starting with the contracts layer. So with the contracts layer, I've already talked about this a little bit, but there's two main things that you want to know. One is the only on-chain contract that needs to exist in a regular state channel, like in one where no one's trying to like screw the other guy over, people are honest, is an on-chain multi-sig. Because you need the ability for everybody involved in the state channel to say, I agree on this. I agree that I will send money in the case of a withdrawal. I agree that if you were to be malicious, we'll be able to go to court, we'll be able to get our money out. I agree on this. It needs to be for every single person involved. Thankfully, this is like a regular primitive that we already see in Ethereum. It's a multi-sig wallet, so it's not that complicated. The complicated stuff is the adjudicator contract, which needs to be able to handle any kind of protocol deviation. We'll be touching on a couple of them I just went over a few a second ago, where if the other party is not responding in the way that is specified by the protocol, you can always go to the chain and in a predictable way get your money out. All that code is, you can see that on the repo later. That stuff gets very involved, and it's very interesting from a theoretical point of view. But that's the second part of the on-chain contract scope. The way we've designed it is not that this works with ETH and tokens. We've designed it such that it works for all possible types of state channel scenarios, right? So ETH, ERC20, it could be CryptoKitties, it could be a plasma cash coin, it could be, literally it could be anything. Because the core primitive that we've designed everything around is not ETH payment or ETH ERC20 payment, it's Ethereum transaction. It's to address the value amount and the data bytes array, which is the most low-level primitive for iterating the Ethereum state machine. That's how the state channel primitive can be built. It's what it's been built around. So anything you can do in Ethereum, you can do in a state channel, provided everyone signs off on it. The types of applications that we can support are state machines. And I'll show some examples. Tic-tac-toe is one. The dice rolling game I showed is one. They're just state machines that adhere to an interface that you're probably already familiar with if you've ever used Redux or something like that, which is given a state, I'll go through each one, given a state and given an action, compute the new state. Right? Tic-tac-toe board and place X equals a new tic-tac-toe board. I have not rolled my dice yet, and here's my dice roll with the randomness that you're going to use. Give me the now of the dice roll. Chess, put my pawn in this position, give me the new chess board. It's a Redux style functional iteration of state machine. Resolve, which is forgive some given state machine at some state. Let's say X is 1. Who actually won? What does it mean for X to be in a diagonal cross? It means that this person gets money. Is terminal, which is just given the state, what does it mean for the state to be done? Tic-tac-toe is pretty obvious. X cross, in any way, that means the game is done. If there's no cross, it's not done yet. So there's a function for that. And get turn taker, which is an important primitive in state channels. You need to know is it valid for somebody to sign a new update or not? And for tic-tac-toe again, it's pretty obvious it's X or O's turn. You can do a lot of cool stuff with this, and you can represent a lot of things that people have traditionally given written papers about and all kinds of great stuff about as state machines. So bidirectional payment channel is the most basic possible case, where you just have some balances array. I have this amount, you have that amount, and you just update it. There's no logic you even need to worry about so much. There's no transition. It's just a new state that you update, and everyone has to agree every step along the way. A more complicated example would be a unidirectional payment channel, where the idea of a unidirectional payment channel is that I send money to somebody else, and they can claim it, but I'm the only person that's allowed to send it. So in that case, it's a bit more complicated. You can imagine that the state machine looks like this. If you're the sender, you can keep sending. If you're the receiver, at any point in time, you can say, I'm done receiving. Again, these are the state machines you can describe. Tic-tac-toe, like I referred to earlier, looks like this. It's X's turn or it's O's turn, and either X wins or O wins, or it's a draw, depending on the outcome. And you can really expand this into really interesting kinds of applications, but these are the most basic ones. So, yeah, we've really tried to make it as simple as possible, and I'll show a little bit of code that shows the simplicity we designed for. So, another example application, counting. Let's say we have a state machine where it's either my turn or it's your turn, and it's my turn, I can either increment or decrement. If it's your turn, you can either increment or decrement. It's a counter. Then the way that this code would look is just like this. It's literally, it's a stateless contract that just says, this is the state that I have, this is what it means to make an action on the state, increment by how much. And you implement the function I talked about earlier, apply action, given some state and an action, what do you do? If it's increment, then you run the increment function. If it's decrement, you run the decrement function, and you return the result. Again, very straightforward. And then the actual implementation is very simple as well. It's just pure functional code. An important thing to remember with state channels is that although Ethereum is a lot of really complicated stuff, state channels can be narrowed down for the most part into pure functional iterative state machines at the moment. Again, you can do some interesting complicated edge case scenarios that we're designing stuff for, but at the moment this covers a large base of the applications people have come to asking for. And you can see the code is very simple to write. It's just given some state, define your state machine, and define what it means to iterate that state machine forward one transition. And you can write this in the stateless Solidity contract. So yeah, I've said it a couple times, but this set of things you can write is all pure functional programs that run in the EVM, which is pretty cool. So that's the contracts layer. The second thing is the actual protocol for state channels. And again, I've referenced some of the stuff already, but the protocol for state channels is it's kind of what I've been talking about, right? It's the messages that you exchange with your counterparty. We've designed all of this stuff, and I think someone asked me earlier, like, what is that actually? You can actually inspect all of this right now at our website, counterfactual.com/specs or specs.counterfactual.com. I think both types work. And it's literally a protocol. So it's what messages do I send to the counterparty? What do they send back to me? How do we actually move this whole thing forward in a way that makes sense? And then finally, the third part is this application library, and we've designed that in mind such that all of these things can be done just by using very simple JavaScript objects. So that looks very similar to Web3, for example, where normally you'd be saying ETH send transaction or contract call function call. Instead, with layer 2, it's just as simple as like, hey, layer 2, I want to update the state, I want to take an action, or some of the things I showed earlier. So yeah, I rushed through that last part a little bit, but I promise I'm done. So yeah, I guess maybe one or two questions, and then maybe we should move forward.
Yeah, just want to know what you think are other applications for state channels besides payments and games. Really, that's all I'm seeing.
Yeah, so the way I like to think about that is it's kind of a weird question because, like, basically anything you can do in Ethereum, you can do in a state channel, right? The only thing you're restricted by is that the state within a state channel can't be shared with the outside world. So that restricts things like marketplaces and exchanges where you have like a public order book that don't have collateralization requirements on behalf of some party, right? Say like the operator of a hub or something like that. The way I like to answer the question is more so, I think any situation where you have the ability to predefine as a machine, which specifically as a machine, how you will behave in certain economic situations, and you can begin to have those machines interact with other machines, that is a perfect use case for state channels. So, like, this is not specifically what I would say is the great state channel example, but it's a type that works. Is like a car going to a garage door and having pre-written software that says, if I encounter a garage door that charges me a penny to enter, I will always say yes. And the garage door says, if I encounter a car that is willing to pay a penny, I will always open the door. and you just seamlessly go in the driveway, the door opens and you enter, but a financial transaction occurs. I think those types of interactions, like machine-to-machine payments based on some interesting conditions that you've pre-codified into your software, I think there's a lot of potential there. You know, another easy example is like mesh networking. Like if my phone had pre-agreed to that if anyone else in this room was willing to give me some data, I just walk in the room and I automatically get data, and that person pre-agreed to sell it to me, and I'm just paying like a penny every like couple minutes. Like that's a great use case for state channels. It's not as obvious as like games and things like that. Cool. Any other questions? Good. Yeah, in front. Sorry. Yeah.
Okay, well, I just wanted, since the things that you're signing are real transactions,
Yeah.
I just wondered why in your demo MetaMask required a signature initially.
Yeah.
Why didn't MetaMask require confirmation of the step?
So in the demo, the first thing you did is you created an account, right? That is basically adding a row in the database of the server. It says that, okay, this is someone that I am willing to interact with. Normally the way people do that is OAuth, or they use password protected like authentication. Because this is like a Web3, app, we use Web3 itself as the authentication layer. So specifically we used your private key in your browser as the signed message saying that you are you. And so we just use it for authentication. And MetaMask happens to have this feature where you can sign arbitrary messages, but it doesn't actually need to be that way. We just did that as a means of using the Web3 tag.
So did you create a separate account for the user, and as far as the Ethereum blockchain is concerned, that kind of new account is the account that's signing transactions?
Yeah, so slightly counterintuitively, Ethereum blockchain wasn't even involved at all. It's just literally we signed a message with our private key saying that I am this public address. And the hub software said, okay, if this public address ever signs a message in the future saying that it wants to like open up a channel with me, then I'll open up a channel with it. So we just use it for authentication. Yeah. Yep.
Something happens to the local storage. How do you get the last time?
If this local storage is like deleted.
Yeah.
Yeah, so like at the moment in the demo, like you're kind of screwed. If your counterparty is nice, then they'll give you their signed copy of everything because they have the same data. If they're not nice, then you're kind of screwed. Which means this software and wallets in particular that implement these protocols need to be like really freaking good.
Would the hub potentially be a place that?
Yeah, I mean it's like at a more fundamental level, you don't have your. It's like saying if Bitcoin, you don't have your private keys, you don't have your money. It's the same situation. You can trust somebody else, and maybe it's a company that has a lot of reputation to lose if they ever cheat you. Maybe they will store it for you. It depends on the marketplace at, but generally speaking, you want to keep your state because you can trust yourself. However, how the market develops, we'll see what happens. I think probably users will keep their own state, but there'll be all kinds of really good software that they use for this.
Two parties interact with each other without the hub.
Yeah, the hub, you and the hub are two parties interacting with each other.
And two users.
Yeah, you and the hub are two. That's like the key point. You're both running the same software. From the point of view of me, the hub is just some other user. Yeah, how many questions can I ask?
I think let's do one more.
Okay, one more question, and then move on. Yeah.
Is there any way to get around the initial lockup of Ethereum or kind of spread it out?
So, like fundamentally speaking, like you need to be able to pre-commit some amount of your money to somebody else, and they need to pre-commit some amount of their money to you in some kind of a contract which says that we're going to follow this protocol, and the money will be dictated by our doubly signed commitments that we both agree on, and how it will be spent in the future. So in some way, you need to put your money. I don't think there's any way around depositing it into some address which is designated as the address that would require those constraints, that you and the person sign things together. All right, cool. There's also just 2 seconds. If you want to learn more, we have a website, counterfactual.com. There's a GitHub, that's the expected URL. The specs that you can read that go into the details of this word protocol I keep using, like specifically what are you sending. And if you want to chat with us in detail, then we have this chat group as well. And if you want to play the demo, You can go to playground.counterfactual.com, and that's it. Alright, thank you.